Hi and welcome back to another short video for the Zero to ASIC course YouTube channel, and today I'm very happy to be joined by Proppy.
Hello.
How's it going, Proppy?
It's fine. Thank you for
Cool,
having me.
Yeah, so could you introduce yourself, please?
Yeah, so I'm Proppy. I work for Google for a little bit more than 10 years now, and I'm based in Tokyo. I'm a developer relation engineer, meaning that I work on improving developer experience for various developer products. And recently I've been focusing on hardware toolchain and more especially OpenLane and the Sky 130 OpenPDK.
And people who've been watching the channel the last few videos probably saw the live stream that we did with Teo recently about optimizing hardware adders. And one of the ways that you made his work more easy was allowing him to be able to do development work in the cloud without having to go through the rigmarole of installing all the tools. And that's what we've got you on today to talk about doing ASIC development in the cloud and looking at your work that you've been doing with Google Colabs.
Yeah.
So what would you like to start off by sharing?
Yeah, so I'd like to start sharing a few notebooks I've been working on and kind of explain the background of why we even thought about running EDA workload inside notebooks. So it's nice that you mentioned Theo. He's on our team as well, and he was one of the first adopter of this kind of EDA in notebook thing or silicon in notebook thing, and the main reason we started with that is that I come from a software background, so I'm totally new to this EDA tooling, in Silicon Flow, OpenLane, PDK. I didn't even know what those words meant a few months ago. That's what kind of shocked me at the beginning is the friction that you have when you want to set up the tool. There is a lot of things that you need to even compile from source, and there is something that are packaged, containers, some other thing that you need to install on your host, and it seems there were at least for me, I kind of got cut off at the beginning by just trying to get started and just facing a mountain of tool to install, and the other, so that was the first thing that we started working on is making sure that we can have some package for those tools and making sure that we can build them in advance and people can install them on their machine and run them right away without having to worry about where to get the source from, which version you should compile. And so that was the first thing. And the other thing that we kind of worked on is once you have this package, making sure you can install them inside the notebook. And the idea of the notebook is that it gives you an environment when you can run code inside a managed environment. And you can specify the code that you want to run. You can add some documentation in Markdown before or after the code that you want to run, and you can see the output of the command that you are running. And the nice thing is that all those data, so the documentation, the command that you need to run, and their output, get serialized inside the notebook themselves. So it gives you a very nice container to share a computation and the result of it with a colleague or a friend or someone that works on your project. It seemed like something that could be fun to do with chip layout, because we do have some needs for visualization. We want to visualize the chip layout at the end, and also there is a lot of metrics to plot. So around performance, area, and power, we can make nice plot and try different settings and see what change.
Cool. So what would you like to start off by sharing then?
Yeah, so I like to show first the first what notebook we worked on. So there is this. So I'm kind of storing currently all those notebooks on my Gist account, and so we're going to figure a better way to share that and having people.
Yeah, we'll put links to these in the video description. So if you're watching and you want to check out these, then you can click below.
Yeah, and so when you go to the Gist, you can click on this Open in Collab thing button there for the notebook that you want. And Collab is basically a managed environment for notebook. It's a notebook service hosted based on Jupyter Notebook, hosted by Google. And you can think of it as Google Doc for notebooks. Like you can get the URL of a notebook, like share it. We click a button, like get a new notebook, like share it with a friend, and like work together on it and make modification. And so here, like when you open in Collab this notebook, like you see like a bunch of cells. And like the first thing that we kind of do is that we install Conda, which is like the package manager that I mentioned before. Let me zoom out a little bit. And which is like a package manager that we've used, and we make sure that like all the tools necessary to go through the ASIC flow are like packaged inside this environment. And then you declare your dependency. So here we say that we need like OpenPDK, Magic, OpenRoad, NetGen, Yosis, and all of those are like Conda packages. And then like you invoke Conda to install like all the dependencies that are listed in there. So here I'm just asking to install the latest version of everything, but here you can also like add some constraint if you wanted, like a specific version of OpenRoad, for example. And then what I do is that I clone OpenLane, which is like just a bunch of TCL scripts that allow you to orchestrate those tools. And then I write my design. Like here in this example, it's like the simplest like design possible, just an inverter. And then like I write the configuration for that design, and then I run through the OpenLane flow. And you can see it's doing like all the OpenLane operation. And at the end of the flow, I display like the layout, and I dump some metrics that are exposed by OpenLane at the end of the flow. So like when you look at it like this, it's going to look like a nice documentation that explains to you how to get started. But you can also like click play here and actually run those operations yourself. And so yeah, it gives you like a sandbox environment that's only for you, and you can execute like all those operations. Like the setup is still a little bit. It takes a little bit of time to like install all the package. It will take like between like 5 and maybe 5 or 10 minutes to just install everything. But once you have everything installed, you can run like the design multiple times and change parameters. And at some point when you don't use the notebook, it gets recycled. And so if you open it, for example, tomorrow after like leaving it idle for a long time, you have to reinstall like the package again. Yeah. I think that's it for the opening notebook. Do you have any question, Matt?
No, that was. I mean, I went through all your notebooks last week because I wanted to get a better handle on how to use them and how to share them with people. So I think that all makes sense. We had some questions when we had the Zero to ASIC group call, like if you wanted to then host this on your own computer, can you do that?
Yeah, so like there is inside the Conda the Collab UI, you can, if you do inside the file menu, there is an option to download the actual notebook file. And so when you download it, you actually also get the output. So you could like also like share this with a friend or open it locally and see the same output. And the thing that you need to do if you want to run it locally is that you want to open it with Jupyter. So you need to pip install like Jupyter inside the virtual env or on your host, and like run Jupyter and open the notebooks that you just downloaded with Collab. There is a few things that you're going to have to change. In particular, like currently, the notebook install everything inside USR local, because that's like where the Python environment is on Collab. But like ideally, if you want to install it on your own machine, you want to install it to the location that you prefer. So usually like a Conda environment that you already like pre-install somewhere, or like a directory that's like that you want to host like your package on. Like you don't really want to clutter like your USR local on your own on your host.
And when I was running it on the Google hosted Colab, it took maybe 5 minutes to get to do
Yeah.
like the first run through and
Yeah.
everything then
Yeah.
set up for me as a local cache.
Yeah.
And then how long does that cache last before I have to
I think
go
it depends
through
on it actually depends on the usage of Collab. If there is a lot of people using Collab at this moment, I think they will be a little bit more aggressive into recycling idle instance. Usually, like I've seen it for my daily usage, I've seen it like timeouting or like being recycled after maybe a few hours or a little bit more than 1 hour. The interesting thing is that like you also have like the capability of either like paying for a subscription for Collab so that like you get like more time and more resources. Like if you have big design that you want to run and you, for example, go over the memory capacity that give you by default in Collab, you can like pay to have like more memory or more time. And the other interesting thing is that you can link a given Collab to a GCP project that you might have, so Google Cloud project, and then you can run a managed version of Collab on the VM of your choice. And so that make it very interesting because you can choose like a VM size in terms of number of core and memory that really fits what you want to do. And like since you control the instance, it never time out when you do this.
Nice. Okay, so do you want to move on to your next demo?
Yeah, sure. Yeah, I just like run like the notebook in the background here, just to give you an idea of what it looks like. Like here we like installed like all the tool, and the thing I'm doing after a while is that I'm cloning OpenLane, and I'm writing the inverter file. I'm writing the configuration, and then running the flow. And here you can see that the flow is running like step by step. Yeah, I just wanted to show you this to see that it's real.
Not just a screenshot.
Yeah. And like the other thing I wanted to show you is like the actual package that we install, because I think it's interesting. So there is this thing called anaconda.org. That's like a repository of package where anybody is free to upload like Conda packages. And like we have a channel on that, and that's called Litex Hub. It's called Litex Hub because it used to host a lot of FPGA related tools. But because we have a good allocation of quota for this channel, we also ended up reusing it for the ASIC tooling. So we're going to try to find a way to rename that to a more sensible name. But for now, that's like the best place that we have to host those things. But some of those tools are actually shared between FPGA and ASIC. So for example, USIS and Renode, like you can use it for both. So like it makes sense also to share some of the tools between those. And the package I personally worked on are the Open Road one and the Open PDK one. So let me show you. Let's look at the Open Road one first. So the interesting thing is that like we upload like basically daily build of Open Road inside this repository. So you are able to like get the latest and the greatest of Open Road with this. But also, if something is broken in Open Road, you're able to go back in time, which is like very useful when you like. There's been like some friction also around like finding the good version when we want to target a shuttle, finding the right, especially more so the Open MPW shuttle. There is fixed version of the tool that usually get tagged that you want to use for a given shuttle, and like and sometimes things get broken, and you need to go back like a few days in time to have a version of the tool that still work. And if you use everything at head, sometimes it breaks. And like having the ability to have like fixed version number and pin your dependency on those versions that you know are working is really useful. And like I've been able to, it's also a very useful tool to test regression, meaning that if you find a bug inside the latest version of Open Road, you can go back in time inside the previous version of Open Road and find the exact commit at which at which, or the exact day where it started failing. And you can more effectively report a bug upstream and say like, hey, I know like this is this commit that created the failure. And we found a few issues like this with Magic and OpenPDK, where it proved really useful to be able to go back in time and really pinpoint the version of Magic or the version of the PDK that created an issue. And so we also have like a package for the PDK. So let me show you. It's on the, yeah, there is the page of packages. And and similarly, like they are tagged after the version number from OpenPDK, and you can also go back in time, and they are relatively small. They only include like what you mostly need for a digital design, so what OpenPDK recommend by default. And all the recipe for the package are maintained inside like this repo called conda IDA, which has like all the recipe for various package for FPGA and ASICs. And just to show you how a typical package looks like, it specifies like where you get the source from. It specifies like the dependency that you need to build the package, the actual dependency that you need to run the package, and then like how you build the package and how you test it. So here I'm just trying to run Magic and print the version to verify that the package is working. And in order to build it, I have a build.sh file that just run configure and make. And like that's like what we do for Magic. For OpenPDK, it's a little bit more involved because you don't have like just one source to get the PDK from. You need to get OpenPDK plus like each of the PDK standard library for the cell that we pack in this package. So we pack SCHT, FD, SCHVL, FDIO, FDPR. And then in order to build the PDK, you need to also like generate the Liberty file. And so that's interesting because like typically as of recently, that was typically done by the user, by every single user that wanted to run like through the ASIC flow. And that was taking like between 20 minutes and 1 hour, depending on the power of your machine. And that was an operation that was duplicated like across like all the users. Like that was part of the onboarding flow to check out the PDK and spend a bunch of time building it. And like often you ended up building also things that we didn't really need. And so the fact that we can do this at build time and distribute like the result of that build process, and just basically just a bunch of files that you just have to extract inside the location with Conda to get installed, or really, really speed up the process. Because like you mentioned before, it's not like you don't need to build that anymore, and you can install like all the dependency that you need to run the flow into around 5 minutes. Do you have any question about the packaging, Matt?
No, I'm just glad that someone else is doing it for me.
Yeah, I mean that was actually like the material for your class was, and the kind of getting started guide that you had were a big inspiration for that work. Like kind of taking what you already documented and making sure that we can create way to find shortcuts, but without really modifying the flow. So, like for example, if you install like OpenPDK package that way, it doesn't change what you need to do afterwards for the other tool. It doesn't necessarily change the way that you install or run OpenLane. It's just like you end up like having an easier way to initialize your PDK route. So trying to find a way where we can speed up this process without being too intrusive into the way people run the flow was also kind of the goal of this. So the Conda package can also be used to run stuff on your host, not necessarily run stuff inside Notebook. They end up playing well with Notebook because it's an easy way to install packages and provision software inside Notebook, but it's also something that you can do on VM or something that you can do on your own computer.
Okay.
Yeah, and but it's still like it's still like a lot of time to install this package, and like you've done something for the class that was also interesting, which was like this VirtualBox image that you share with people. That like they have a VM that has everything in it. And reusing the work that we've done on the package, we've tried to do like something similar on GCP. So maybe I can show you that next.
Sure thing. What's GCP?
So GCP, it's Google Cloud Platform. Yeah, I should say
Okay.
Google Cloud. Yeah. And so, let me show you like that thing. So we created like a RadLab module for silicon design. So RadLab is a fancy name for basically a bunch of Terraform recipes that allow you to initialize like some resource inside your GCP, your Google Cloud project. So Terraform is like a configuration system for infrastructure as code. It allows you to define like, I will show you, it allows you to define like a VM, network, Google Cloud Storage bucket, like all the resources that you will normally create within the Google Cloud UI with the console with like many clicks to create all those things. You can declare inside a configuration language and execute the recipe, and it ends up creating all of those resources. And like when you modify those recipe, it will like get the current state of your project and try to reconcile it with your new configuration. And so we created like a recipe that basically allow us to run the similar notebook that we have on Collab, but on your own project. And the other big difference also is that it pre-provision like all the software, all the tool, all the package inside the notebooks and inside the VM images. So that like instead of spending like those 5 minutes to install all of this package, you already have, when the system boot up, you already have an environment that's already all set up. And so like when you deploy it to your project, it looks like this. You have like a Jupyter Lab UI with some notebooks that you can open. And like here you can see it's like basically the same notebook that I had before in Collab, but a simplified version, because inside this notebook, like for example, if I create a cell here and I tap which open road, I already have open road installed. If I create magic, I already have magic installed. So I have like all the tools that are already there right when I start the notebook. And so it's allowing me to get started more quickly. I can define my flow parameter, define the design that I want to run, and the configuration, then run the flow. And similar to the thing that we were doing before, you can display the layout, dump the metrics. And here I do something, I do a little bit more thing at the end, which is I'm trying to extract the power metrics for the design and like try to plot them inside a fancy table. And so that like I'm able to see like the power consumption for the design that I generated. So here I put the design, I do metrics, and I extract the power. And here you can see that I have multiple lines there. I basically have one line per time that I run the flow. So instead of just putting like the latest thing that I run, it plot like basically all the run that are inside this run folder here. So every time you run OpenLane, it creates like a different directory. And so this creates like a table with all those values. And like, so it allows you kind of to play with those parameters and kind of like get some immediate feedback and immediate result on the effect on the layout, and also measure like things like power consumption or performance, and see like how those parameters affect like those metrics. And like the interesting thing too is that like we have a way to basically tag like this cell and say that this cell defines some parameter for the notebook. And what it allows us to do is to then like call this notebook programmatically from the outside with some parameter. So basically, without modifying the cell by hand, we can call a program use a program called Papermill to you reuse the notebook basically as if it was a standalone tool that was capable of just executing that design. And we pass the parameter that we want. And the interesting thing is that at the end of executing that, we get another notebook that has like the result of our computation with this parameter. And yeah, do you want me to talk, Matt? I don't know if you have more questions on that, but
yeah. So is that the thing that you were just mentioning? Is that the feature that lets you do these huge runs that you've been doing?
Yeah. So like there is like a so you know how you usually like when you write software, you write function, they take parameter, they return value, and like there is a way to do something similar with a notebook. So like the parameter that I mentioned is a way to pass parameter, and there is also this thing called a scrapbook that allow you to attach value to the notebook. So as you do computation, like you compute value that are inside the Python context of the notebook. But when you close that notebook, like all that Python context that was in memory is lost. And so the only thing that you have remaining in the notebook are like the actual cell, the command that you were running, and the output. But you don't really have a serialization of the state of the memory as of the last time that you opened the notebook. And so if you share a notebook with someone, they wouldn't have access to the same data. They will have to run the same computation. But there is a way that there is a little tool called Scrapbook that allows you to basically checkpoint and serialize anything that you have in memory at any time of the notebook inside a key value structure that's also attached to the notebook. Meaning that afterwards, like you can open the notebook as a file and inspect it and see, enumerate like the value that were attached to it and be able to get them.
Nice for debugging and reproducibility.
Yeah, exactly.
Yeah. So
like,
maybe now we should move on and talk a bit about the work that you've been doing with Serve.
Yeah. So like that was like the design I've shown you there was like for something very simple, like an inverter. But I can show you like what a more complicated design look like. So here we have like basically the same structure for the notebook, but instead of having something that that just write a Verilog file to the current directory, I have something that clone a serve, which is like a RISC-V serial call that's very small and serial, and the subservant, which is like basically a SOC wrapper around that SOC to like actually put it into a real functioning chip around that core, to put it into a real functioning chip. And similarly, I define like some parameter, base parameter, not so here, like because it's a more complex design, I wanted to give it a little bit more space. And I can similarly like run the flow and the core. It's not running because I didn't load it, of course. And now it's running like the flow on Serve. It's going to take a little bit more time, but at the end of the flow, you get a lot of outputs, but you get like a pretty design. So here you can see like the Serve SOC. That's kind of it's very compact and it has a lot of area around it. And similarly, you can plot power and depending on the parameter and depending on the density that you add. And you can play with parameter locally, and it only gets you so far as your motivation to change the parameter and wait for the result and tweak them. And so like the idea that we had around this was that like since we are, like I explained before, we are able to call those notebook with parameter from the outside and get value about like the computation that was run and the status of those metrics. It was a natural next step to spin up a bunch of VM and like run all those experiments with different parameters concurrently, so that we can explore like all the parameter space for that was for like the diarrhea and the density, and find like what are the good design within that area that produce like the better power consumption. And so like that's a big parameter space to explore. And like if you do it like linearly, you will have like a lot of failure, and it will take you some time to converge toward like the actual like sweet area where this where the actual design produces a better result. And you might end up losing a lot of money and computation time trying to find that space. And so for that, like Google Cloud as a service, it's also an open source project, but it's also a paper that they published like a few years ago called Vizier. And it's a black box optimization service that basically it doesn't care about what kind of computation you want to do. You just specify like some parameter range that you want to explore. You ask him for like a sample of, I don't know, 10, 50, or 100 parameter that you should run. It gives you the parameter, you run the computation yourself, and then you specify the metrics that you want to optimize for, and then you give him the metrics result for those computation that you run. And then what Vizier will do for you is that next time you ask him for 50 more or 100 more parameters, it will give you a parameter that he think converge toward the goal that you express, which is, for example, in my case, like minimizing power. So it allows you to converge like more quickly and get a smarter parameter suggestion for the run that you want to run, that you want to execute, and spend less time exploring space that doesn't need to be explored to produce like the metrics that you are after. So I can show you how we do that. And of course, we do that also inside a notebook. So we have like this tuning notebook. That's about you taking a notebook that you already written for one experiment and like running it again and again with parameters that are suggested by Vizier to find like the best metrics. So you could do that by calling the Vizier API inside the notebook itself, and it will be a little bit involved. But the interesting thing is that like Google Cloud has also a service to do this parameter optimization automatically for you, but they label it as something to train ML model. But it actually doesn't really care if the thing that you are running is a ML model or not. So here we are just pretending that we are tuning an ML model, but we actually run an EDA workload. So we disguise our EDA workload as a ML training job, but that allows us to get the functionality of parameter tuning, get access to the parameter tuning functionality more easily. So that's what I'm doing here. I'm saying that I want to create an hyperparameter tuning job, and that I have two parameters that I want to explore, target density and die width, and I give like the range for each of those parameters. And I say that I have like one metric that I want to optimize for, which is total power. And I stage my notebook that I want to base my experiment on Google Cloud Storage, and then I specify that I want to run a job on N1 like form VM, and that I want to run it with this paper mill thing I was mentioning before, which take a notebook as a parameter and produce another notebook as a result. And that thing will be called with like those parameters that comes from the suggestion from Vizier. And then I just specify that I want to run like 10,000 of those jobs and run like 50 of them in parallel. And the reason I don't run, I have a smaller number here for the number I want to run in parallel versus the total number that I want to run, is because like I want to make smaller batch so that like between all those batch I get new parameter suggestion. So basically leave some space for Vizier to breathe and give me suggestion on what to run next. And like after you run like that thing, you end up with a bunch of notebooks. So I can show you quickly here. You have like 10,000 notebooks that were created by this job, and like it's like consuming, I think 1.5 gigabyte. And the nice thing is that once we have this notebook, we can like do more aggregation, like do some stats, like produce nice images. So maybe, I don't know, do you have any question, Matt, or do you want me to jump inside the visualization?
No, I think just keep going and jump into the visualization.
Yeah. So like
maybe just show the little file folder thing on the left hand side, because that was interesting for me.
Yeah, that's like those like basically all those notebooks are named after the trial, so the experiment that was run with like a specific parameter. And so if we open, for example, here notebook 6037, you can see that what it actually did, we still have the parameter that we had originally inside our experiment, but it inserted the paper mill, the tool inserted a new cell in there with the parameter that were suggested by Vizier. So here, like we have a very like big die width and a density that's lower than what we were using inside our first experiment. And you can also get like the full output of the flow, because it's like a notebook, so it's serialized like its output. And you also get like the actual layout and the summary. And you can see here I have like this little call to scrapbook.glue, and that's the thing that I was mentioning before. That's attaching metadata to the notebook, so I can like introspect them from the outside after the experiment is run. So I can, for example, I can get access here to the data frame that's based on the CSV that come out of OpenLane, or I can here access to the actual PNG file that was produced at the end of the flow. And the other thing that's also interesting is the power metrics that we compute at the end, I also attach to the notebook. And the last cell here is for reporting the actual metrics that we want to optimize, the value for the metrics we wanted to optimize for to Vizier. So here we, at the end of the flow, we tell Vizier, like, for this experiment, for those parameters, that's the total power I got. And then this will help Vizier to make better parameter suggestion for the next run. And so once we have like all those notebooks, we can read them. So there is like this scrapbook function that takes a directory and read like all the notebooks inside this directory. And yeah, like it's 10,000 notebook. And once you do this, you can like aggregate the data that's inside those notebooks. So for each of the notebook that you open, you can access the scrap. So basically anything that you glue to the notebook is accessible inside this key value. And here I'm just accessing it and printing a table that show for each trial, like the area, the target density, the total power, and the total cell area. And it sort the value by total cell area. So it sort the value by utilization here. And I think it drops the duplicate when the power is the same. So okay, if you run that, you can see it's reading the 10,000 notebook and like producing this table. And you can slice and sort the data as you want. Like here, for example, I'm printing the smallest die first. So you can see here like the area is getting bigger, bigger, and bigger. And you can also like do plots, which I think is interesting, which like you can do a scatter plot of like the area as the x-axis and the target density as the y-axis, and then use a color to specify the power of the experiment. So each of the dot that you see here is actually like a VM that runs somewhere with some parameters suggested by Cloud Vizier, and like and that run like the EDA flow for that design. And we can also plot the value for the run that didn't work. So here we see like all the run in black that actually didn't work. And like if we use some alpha, and then like get some idea of where Vizier like concentrated concentrated the design exploration. So you can see here that a lot of those like good low power run were located inside that area. I kind of have this rift where you have like something that's not super dense, but that's not super large either. It's kind of reaching a sweet spot between the two. And yeah, that thing was also interesting, like to produce a GIF that show like all the experiment by batch of 50, so as they got scheduled, and you can get a sense on how the parameter space is exploration is progressing. And you see, like, yeah, it's actually converged like pretty quickly. So we really didn't need like to run like 10,000 things to get like the best design. Like we could have run I think a couple of hundred of run and have already something that's good enough. It was still interesting to see what's happened when you actually run 10,000 of those. And like the other thing,
it gives like a bit of an insight into how the tools actually work.
Yeah, and that's the thing I really want to also see, is to be able to see like all the different design that got produced. And so like here I did like a little animation of like all the layouts. So similarly, I'm extracting the layouts out of, you can see here, let me show you that. I'm extracting the actual layouts from the thing that gets scrapped. So here, like there is a scrap layout that has a base64 encoded version of the image. And then I'm basically drawing it with 3 rectangles, which correspond to the density, the area of the power of each design. And I'm sorting those design. So we did a little bit of back and forth with Theo on trying to find like what will be the way to sort those design to have like the smoothest transition, so you don't really have design that so the design between frame, the difference between design is like smaller. And like we landed on using cell total cell area for that. So we divide like basically the area by the density that we pass as a parameter, and that allow us to kind of get design that are that have similar concentration, so that kind of look like each other. And so you slowly like move toward like design that are more and more dense and smaller, and like with also like better power utilization. So maybe I can show you like that. I did post like just like try to post this on YouTube so we can get like a timeline and kind of see inside of it. The resolution is not that good compared to the GIF, but I think that's okay. I think the interesting. So at the beginning, it doesn't move a lot. It moves a lot at the beginning, but it kind of stabilize, and you get like this very boring part. It will be funny to annotate it actually with chapter. That will so that like you can scroll directly, seek to the interesting part. But toward the end, it gets very wild. So I think like when it starts to get at 30 minutes and 40 minutes, like that's where like it's the design like start to get really interesting. And we get like something that's being more and more spread out. It gets like really funny around like 14 minutes, or like it just spread and start taking the whole die.
Cool.
Yeah. And you can see like the thing that we had at the end is like very different from the thing that we have here, for example. So yeah, I will try to get like a bigger resolution thing. I think the actual layout image that we have are 3000 by 3000. So we could get like a 4K version. Not as blurry.
Great. Well, thanks so much for taking us through your work, Proppy.
Yeah,
really appreciate it.
Yeah.
And how can people get in touch with you if they want to find out more?
Oh yeah, so like I'm on the 02 ASICs Discord. I'm also on the Skywire Skywire Slack. So yeah, join.skywire.tools. We can add the link to
I'll put the link to that as well.
Yeah, and I'm Proppy on both. So, and I'm also like on Twitter, and my LDAP is Proppy there, and on GitHub I'm also Proppy. So like yeah, on all those things you can find me with that name.
Great.
And
Okay.
I'm like, if anybody wants to try to reproduce that with their design, like I'm happy to walk them through the process of deploying the solution to their project, or even like if they have like a collab notebook that's working, I can easily show them how to convert it to run it on this managed solution, so that we can do interesting design exploration for that design. I know that a lot of people are kind of during the last week of the MPW shuttle, Open MPW shuttle, like everybody is like racing to try to get
Try to get their design to fit. Yeah.
to fit, and so that could be like a way to take a shortcut where while you are sleeping, you get like this design working for you, and then when you wake up, you have like a
The best
design that
parameters.
exactly fit the area that you wanted.
Nice. Great. Okay. Well, thanks again, Proppy. And
Yeah, no problem.
I'll see you around.
Yeah, see you. Bye. Thank you.
Bye-bye.